My big question for you
Uh-oh.
is, if you had the chance to have any mystery of the universe solved, the answer right in front of you, how something that we don't understand actually works, what would you pick? I'm Talia Sepersky, a planetarium educator here at the Museum of Science. Today, my guest is Dr. Paul Sutter, theoretical cosmologist, author, and renowned science communicator. I get to ask him about whether we're alone in the universe, about some of the ways space can kill you, and about some of the major issues facing science today. Paul.
Yeah.
You are a very prolific article writer. You write a lot of articles.
I do.
And I get to read a lot of those as I'm going through looking for stuff to include in the museum's space newsletter, Spacing Out. You wrote one fairly recently that kind of boggled my mind a little bit.
Oh, okay.
And it was about the idea of life being able to thrive without a planet.
Yeah. One of my favorite things about writing articles like these is getting to serve as a bridge between scientists who are writing journal articles with an audience of other scientists in mind with the general public. Because if I only talked about my own research, I'd be done in just a couple months because my own research takes a very long time, and I'd talk about it and then that'd be it. So I love getting to share what my colleagues are working on. And so what I do is I peruse the latest articles. And in fact, almost all astronomy and physics articles are available for free online worldwide to anybody through a website called the Archive. That's ARXIV. It's been in operation since the early 90s, since the beginning of the World Wide Web. And almost every astronomer and physicist puts their articles online on this server, regardless of publication status, whether it's been approved or it's still pending peer review, anything, it just goes on there. And so I like to browse it. I get an email every day with that day's batch of submissions, and I flag interesting papers. And then interesting papers I get the opportunity to write about. And so there was this particular paper which talked about just habitability and challenging some of our assumptions of habitability, like where can life live? And even when you think of like the most extreme forms of life, the most diverse forms of life imaginable, we tend to think of those life forms as planet bound because planets are super handy. There's a place to plant yourself. Literally, there's air contained by the gravity of the planet. You're protected by solar radiation, by that atmosphere, and so planets make for great places for life. But this paper challenged that assumption, saying, what if life could generate its own biosphere, free floating in space without a planet?
It sounds crazy. Like
it is crazy.
Yeah.
It's absolutely crazy, and it's probably wrong. My own personal mantra is, if it's interesting, it's probably wrong, because the most interesting science, the most eyebrow-raising science, the one that can create headlines, the one that will garner the most public attention, is probably wrong because that's just the way science is, and the way research goes. But it's still worth talking about because wrong ideas are still useful, and potentially wrong ideas are still useful. In this case, the paper outlined a strategy of a list of requirements of what life would require in order to have a self-sustaining biosphere without a planet. And these ideas probably don't actually work out in the universe, but it's good to think about it.
And to be clear, when we're talking about, these theoretical crazy life forms living in space, we're talking about them like actually living and thriving in space, not just surviving the way, you talk about tardigrades on the outside of the International Space Station. They are still alive out there, but they're not, forming tardigrade colonies.
Exactly. We're not talking about like a dormant spore tucked in a crevice of a comet. We're talking about a self-sustaining habitat, say 1,000 kilometers across, that is purely made of organic matter, of almost like a terrarium where it's all self-sustaining, where all the cycles take place inside of it, and there's recycling of energy and nutrients from one life form to another that have built themselves up to be a free-floating biological thing.
I feel like there was an episode of Star Trek about something like
There's
this.
an episode of Star Trek about just about anything.
true.
They had very creative writers, and but it's good to take those creative ideas from science fiction and make it a little more rigorous to see if we can push the definition of life and habitability.
So since we're on the subject of, life out in space, which of course is frequently in the news, has been in the news more recently because they're doing, the hearings again in Congress about UAPs because, we call them UAPs now. UFOs is like last century.
So old school. We don't
So
do that
old school.
anymore. No.
For those who don't know.
Yes.
UAP stands for Unidentified Aerial Phenomena, and it's apparently the new UFO.
Mm-hmm.
And when you're thinking about life out there in the universe, what is your opinion when you're thinking about, like, we're pretty sure it exists?
Well,
right?
I mean, that's the thing. Like, scientifically, based on all available evidence, we are alone in the universe.
Well, that's a depressing statement.
I know. Like, I'm a total buzzkill when it comes to this. We have no evidence. We see no signs of life outside the Earth. We see no evidence of microbes on the Martian surface. We detect no radio signals. We see no techno-signatures. We don't see any, advanced civilizations building gigantic structures and transforming stars or entire galaxies. We don't. As far as we know, we are alone. Now, the search isn't over. We're not done looking. It's a big universe out there with hundreds of billions of stars in the Milky Way galaxy and like 2 trillion galaxies in the observable universe. So we've just barely scratched the surface. But taking that away, taking the evidence, which is as far as we know, we are alone. I don't like to think that way.
No.
So personally, taking off my scientist hat and putting on my human being hat that looks out at the night sky, looks and thinks about the cosmos, thinks about the vast enormity of the universe, I don't like to think that it's all just for us. That makes me feel so scared and so alone. And so to help me sleep at night, I like to think that there is other life out there in the universe. But that's not based on any evidence. That's just based on warm, fuzzy feelings.
So this brings up something that I always think is fun to ponder, and that is the Fermi paradox.
The Fermi paradox.
And again, this is the idea that it's the question, where are all the aliens? Supposedly brought on by legendary physicist Enrico Fermi, sitting down to lunch one day with a bunch of his fellow physicist friends and going, where is everybody?
Where is everybody? Yeah.
Now, a lot of people have come up with a lot of different answers to the Fermi paradox, some of which are really fun, some of which are really depressing. Going back to Star Trek, my favorite one is probably the Star Trekiest one, which is, the prime directive.
Like the zoo hypothesis, where
more like prime directive, where they're just waiting for us to get interesting.
Okay. We're sorry, universe. We're not interesting.
We're not
yet.
interesting enough yet. Do you have, when you're thinking about, this idea that there are statistically probably aliens out there, do you have a favored reason or a favored solution to the Fermi paradox?
I do. And it's that the Fermi paradox doesn't adequately address the true time and spatial scales in the universe, where the Fermi paradox arises because we assume that if life is common, which is a decent assumption because life appeared here on Earth and the universe tends not to do things only once. And so if it appeared here, it probably appeared elsewhere. The assumption is that if life has appeared elsewhere, we would be able to detect it. They would leave their mark. They would, carve a giant smiley face or their equivalent of a smiley face in the surface of their star or something. But when we truly account for interstellar and intergalactic distances, this is something beyond what our human brains are really capable of envisioning. Yes, we have the mathematics. We can write down the numbers in light years or parsec or kilometers, whatever unit you desire. We can write this stuff down. But that doesn't mean we can actually mentally encapsulate it in our heads. And so I do think there are other intelligent civilizations out there based on just, like I said, just me wanting to sleep at night and not feel so lonely. But the distances between stars are so vast, and the amount of time it takes to reach one star to another, even for signals to propagate, is so long and so vast that we are effectively alone. That you could have civilizations that last for millions of years and reach millions of stars, and we would never know about it.
So what you're saying is the United Federation of Planets could just be like a couple of nebulas over.
It could be like right over there. But even our most powerful radio broadcasts, the ones that can swamp the Earth, by the time they reach our nearest neighbor star, they're indistinguishable from background noise. That's how isolated we are and how vast our galaxy is.
Space is pretty insane.
Space is big.
Space is very big. It's true. So shifting from life in space to death in space.
Okay.
You wrote a book in 2020 that has a really incredible title, How to Die in Space.
How to Die in Space. Yes. This was a very fun book to write.
I want to talk a little bit about this book. All right. So how to die in space. Is this an instruction manual? Is it?
It is not. It is an excuse to talk about some really cool astrophysics. So the through line, which is very, very thin, is you are an explorer going out about the universe, wanting to study and understand things. But it turns out that most everything that you are interested in is in some way dangerous. And so it is a guidebook to help you avoid those dangerous things by describing the horrible ways that it will kill you.
Do you have a favorite way to die in space?
My favorite way to die in space is through cosmic string.
Ooh.
Yes.
Cosmic string.
Cosmic strings are purely hypothetical. We don't know if they exist, but they are predicted from many of our theories of the very early Big Bang. And these are hypothetical defects in space-time. They're cracks in the universe itself that are no wider than an atomic nucleus, but they would stretch for hundreds of millions of light years on a side. They would warp gravity in very, very strange ways. They would deform space-time so that if you went in orbit around it, by the time you completed a full circle, you would not go 360 degrees. You would fall a little bit short because of the distortions in geometry. They might glow, they might emit high energy radiation and particles, depending on how they interact with the rest of the universe. But they would essentially cut you in half and they'd be totally invisible, which is pretty fun.
Well, at least, it'd be quick.
It'd be quick and relatively painless.
There you go.
Yeah.
And really, what more can you ask for?
Yeah, that's maybe surrounded by your loved ones. I suppose.
Although I gotta say, I think my favorite way of dying in space is probably spaghettification.
Spaghettification, always a classic. Falling into a small black hole before you even touch the event horizon, you're stretched out like a thin strand of spaghetti.
If nothing
always
else,
a hit with the kids.
I just feel like being able to put died by spaghettification on your tombstone is just a way to make everybody happy.
Yes.
For future
died like you lived, enjoying spaghetti.
Your research specifically, the thing, what your PhD is in, is vasty out there.
Vasty out there stuff. That's what it says on my diploma, actually. A doctor of vasty out there stuff.
It should.
I'm a cosmologist, which is a branch of astrophysics, which is a branch of physics, which is a branch of philosophy, where I study the universe as a single physical object. So I study its history, its contents, its evolution, and try to predict its future, try to figure out how everything in the universe connects to each other at the very largest of scales.
Awesome.
Yeah, so super easy.
Just, whatever. Yeah. Just the entire universe. No big deal.
No big deal.
Going back to all your writing, it covers a huge range of topics. You write about human spaceflight. You write about, just in the last couple of weeks, you've written about Mars. You've written about black holes. You've written about supernovae. You've written about a very wide variety of topics. So do you have like a favorite subtopic of
Yeah, besides
Space.
my own research.
Besides your own research?
Okay, because my own research is
Yeah.
right at the top.
Besides
because,
the vasty.
the big vasty stuff. I'm always a sucker for exoplanet stories.
Oh, I love exoplanets.
Exoplanets, the wide variety of exoplanets. Exoplanets are so hot right now. It's a huge and growing field in astronomy. A lot of young researchers are coming into the field wanting to study more about exoplanets. And we're just discovering like crazy, crazy planets we never thought could have existed. You go back 50 years and you survey like science fiction authors or the worlds they imagine. It doesn't even come close to what nature actually produces, which is wild and really fun.
Exoplanets are one of my favorite things to talk about in the planetarium, especially if I've got kids in there and get to talk about all these crazy planets because we're finding them at insane rates.
We are. We had the Kepler Space Telescope, which found something like 5,000 exoplanets. Now we have TESS, NASA's latest satellite, which is finding fewer because it's designed more differently. It's targeting more. The James Webb Space Telescope is giving us a lot of detailed information about some of these exoplanets. And then upcoming, we have the Nancy Grace Roman telescope, which is going to find millions of exoplanets. And then hopefully coming up after that, something we're working on next is something called the Habitable Worlds Observatory, which is like a super James Webb, which is going to target just around a dozen exoplanets, but give us very, very detailed information and especially search for biosignatures, which is evidence for life on those planets.
Well, because this is one of the things that, like, we're very, very good at finding planets out there, but so far we're only like so at like saying what those planets would actually like being on the surface would be like.
Exactly, because planets in general are kind of small and they tend not to glow very brightly on their own. There are some cases where we have direct images, actual photographs of exoplanets. If it's a very, very large exoplanet like Jupiter size and it's pretty warm, we can actually black out the light from the star and see the infrared glow of the planet, the warmth of the planet itself. We can get a picture of it. We have a few of those, but those are very few and far between. In most cases, we don't even see the exoplanet as a dot of light. We only gather evidence for the existence of the exoplanet based on what it does to its star. So if that exoplanet crosses in front of the face of a star, it dims the light from that star just a tiny, tiny bit, and we can tell that there's an exoplanet in the system. Or if the exoplanet is orbiting around the star, it tugs on that star and it makes the star move around a little bit, and we can look at the shifting of the light caused by that little bit of wiggle. So we can identify where exoplanets are, and we can start to get some basic information about them, like their distance from the star, their size, sometimes their mass. But then that's basically it, unless we do a lot more work.
One of the big goals for the hunt for exoplanets is to find a place where a biosphere could exist.
An Earth 2.0.
And apparently, maybe it doesn't have to be
even a planet. Yeah.
But we're also like finding all sorts of crazy places in our own solar system that we think could potentially support life, but look absolutely nothing like the Earth.
Absolutely. And that's one of the most exciting things is how our own solar system is teaching us about habitability and the possibilities of life in the universe. Because we look around the solar system and we're the only place that we know of where life exists. So we assume life, planets that host life look a lot like the Earth. We know Mars was once a very Earth-like billions of years ago. And so that's why we're very excited by Mars, because we might dig up some evidence of microbial life in the ancient Mars. But now we're finding places in our own solar system that have the conditions for life and yet look nothing like the Earth. So the big ones here are the outer moons, the moons of the giant planets. So we're talking Europa, Ganymede, Titan, moons like that. Enceladus is another great one, where they are covered in thick layers of ice, and then underneath their ice, they have liquid water oceans. In some cases, liquid water oceans that span the entire globes of these worlds, and in fact have more liquid water than the Earth does. And we know that life as we know it requires liquid water, and there are like a dozen places with liquid water that we would have never thought of before.
So if you had to predict, looking ahead at the study of exoplanets, when we're going to be able to look at a world and say, you know what, that's an Earth.
We are honestly hoping to have a statement like that sometime in the next 20 to 30 years.
20 to 30, all right.
20, you got to think NASA timelines here. Because it won't be this generation of telescopes. It won't be the James Webb. The James Webb is not powerful enough to give us that precise information about the chemical makeup of an alien atmosphere to tell us if there's life or not, unless we get extremely lucky, which would be great. But if we're not lucky, we just have to build an even bigger instrument and be more careful and more detailed with our observations. We have to wait a whole other generation.
Bigger than Webb. Wow.
Bigger than Webb, like a super Webb.
Super Webb. Yeah. I'm going to call it Spider-Man.
Yeah, exactly. Yeah. Spider-Man's Webb.
Spider-Man. There seems to be very little that Webb can't do. It looks at planets in our own solar system. It looks at worlds within our own Milky Way. It looks at the very, very distant reaches of the universe, out in the vastiness where your
out in the vastiness
where your research sort of focuses. What you just mentioned, what it can't do in terms of like finding an Earth, unless we're very lucky. What else can't it do?
It can't teach us about love. It can't give us a good recipe for a frittata. There's a long list of things that Webb can't do. No, Webb is a great multi-purpose observatory, but it does have its limitations. It is an infrared telescope. It does not look at the visible spectrum of light. It doesn't look at radios or X-rays. It looks primarily at infrared. And this gives it access to exoplanet atmospheres, gives us access to star-forming regions, and it gives it access to the extremely early universe, like some of the first galaxies to ever appear on the cosmic scene billions of years ago. But it's because it's so big, and has such high resolution, it has a very, very narrow field of view. It's a very targeted instrument. It's like a pinpoint, like laser looking at the sky, where you look at one little target and get a lot of information about that one little target. So you look at one distant galaxy or one distant exoplanet. It's not a very good survey instrument.
And correct me if I'm wrong, that's going to be sort of the specialty of the Nancy Grace Roman telescope,
That's
correct?
exactly the specialty of the Nancy Grace Roman telescope, and also the specialty of the European Space Agency's Euclid telescope, which recently launched. They're going to have very similar and somewhat overlapping capabilities. And the purpose of these instruments is not to go narrow but deep, but shallow and broad, to build up a large catalog of objects where we know less about each individual object, but we get to collect a lot of them and build some interesting statistics.
So we've got new telescopes launching. We've also been launching some, really exciting missions to some of those outer moons, and missions to asteroids. Do you have a mission, whether a telescope or a planetary spacecraft or whatever? Do you have a mission coming up that you're super excited about?
What I'm excited about all of them, because I just by default geek out about every launch, every space probe, every craft that we send into the solar system.
I feel that very strongly.
I am excited by the plans right now for the Dragonfly concept. Yes. This is the Titan hovercraft kind of thing.
The octocopter.
The octocopter that is going to fly around the atmosphere of Titan, which is the largest moon of Saturn, which is one of the few worlds in our solar system to host a significant atmosphere. And it's a moon, very, very far away from the sun, extremely cold, like a temperature of like negative 200 something Celsius or Fahrenheit, it doesn't matter. And yet it has a thick atmosphere. It has lakes and seas and rivers and streams of liquid methane and propane and other hydrocarbons. And okay, this is an interesting place. Just the bare fact of its existence is interesting. Also, there might be a liquid water ocean underneath the surface, because there isn't enough.
Extra.
Because Titan's kind of a show off that way. And Titan is especially interesting because once again, we are pushing the boundaries of habitability, pushing our boundaries of the possibility of life. Because life as we know it requires water. You need something to play around in. You need a bath of neutral bath that you can play around with and have all your chemical reactions. Hydrocarbons might also do the trick. Might also be a fundamental basis for life, a solvent for life to do its living things. We don't know. We can't exactly figure out how life would work in such conditions, but it might be happening right there. So let's go check it out. Let's send 10 dragonflies. Let's go. Let's do it right now.
I think that's probably the one I'm most looking forward to as well. My big question for you is, if you had the chance to have any mystery of the universe solved, the answer right in front of you, how something that we don't understand actually works, what would you pick?
So I have to pick amongst, like, are we alone? What are the secrets of quantum gravity? What was the extremely early universe like?
Them's the rules.
Turbulence. Why is there turbulence? We don't understand how turbulence works, by the way, which is always fun. Okay, that's not a fun question. I don't like that question because I have to pick and I only get to answer one of these. Let's go with, you know what? Actually, I would put, like, are we alone?
Okay.
At the top. I'd like to know. The other stuff, we are making progress year by year. Mm-hmm. And honestly, in physics, every time we come up with an answer, like, we generate a million more questions. Like, so we figure out quantum gravity, then there's something else we're going to have to figure out after that. But at least, are we alone in the universe? At least it's binary, yes or no. And then, there's a lot of processing we'd have to do with that answer, either direction. But at least it'd just be binary, crystal clear, and just yes or no. So I'll go with that.
Something that had, once we know it, is an easy answer.
Yeah, exactly. Did I get it right?
Well, there is no right answer.
Oh, okay.
I don't know how to break this to you.
Okay.
Technically, you could have said turbulence or quantum gravity, and it still would have been right.
Okay.
So I'm gonna shift tone just a little bit to talk. Not that I don't love nerding out about the possibilities of life in the universe, but I want to talk about your new book, which is called Rescuing Science, which is kind of a provocative title.
Yes, it is a provocative title, but there's a life preserver on the cover.
There's
a little bit of hope. A
little life ring.
Yes. Rescuing Science, Restoring Trust in an Age of Doubt.
That sounds like a big topic.
It was a big topic. This was by far the most difficult book I've ever written. And I've written about quantum mechanics. I've written about the Big Bang. I've written about turbulence.
I mean, that's just tough physics.
It's all physics. And like, I knew physics, or at least I pretend to. Like, I at least went to school for it, and I practice it. Rescuing Science was a much more personal book. Because this was a very introspective book. And I wrote this book. I actually wrote the first draft of this entire book in the summer of 2020.
Oh, so, a nice light
It's a COVID baby. Everyone has a COVID project. Some of us took up sourdough bread making. I wrote a book. And the book was, as I was watching public trust in science erode before my very eyes. I was watching it on the news. I was reading it in the news. I was seeing it in my community, where scientists were coming up on TV saying, hey, I think you need to do this. Or scientists going on TV and making mistakes, like saying, we need to do this. And then it turns out we didn't need to do that, which is okay because that's the way the evidence goes. But like, the scientists weren't explaining that very well. And I was seeing trust in science erode. And this is borne out by multiple surveys where over the past 4 years, trust in science has collapsed. And I wanted to address it. I wanted to dig in. I wanted to talk about, why is the public, in a moment at a time when we needed the guidance of science the most, why were we losing trust? And specifically, I wanted to take this from the perspective of a scientist, from a community of scientists. From the outset, I don't know how to change people's minds. If someone doesn't trust science, I don't know the magic formula to get them to trust science again. But I want to make sure that everything I'm doing as a scientist and as a science communicator is doing everything I can to create the opportunity for trust, to at least build a bridge. I can't make someone walk across the bridge, but I can build it. And so this book is a very critical look at the relationship between science and the public, and especially about the shortcomings of what scientists do and how they treat and interact with the public, and how this may have led to erosion in trust, and then how we can get it back.
And what were some of those shortcomings that you sort of noticed pop up a lot?
One of the biggest shortcomings is a total failure of the scientific community in general to engage with the public in a significant way. Most scientists spend most of their time not communicating with the public. And at some level, that's okay. We need scientists to be doing research, running experiments, developing theories. But a professional career in science, the more you engage in science outreach and communication, the more you engage with the public, the more it hurts your career. You make yourself ineligible for promotion, for hire, for tenure, for grants, for all the things that you need to do to continue your career in science. I was told this personally as I started to explore more in the area of science communication and engage with the public. My colleagues would stop me in the hall and tell me to stop, and tell me that I was putting my entire career at risk the more I was engaging with the public.
Was that just because of the time you were investing in it, or was it some other aspect of it?
Time and snobbery.
Snobbery.
Any amount of time you're not writing papers or chasing grants is a waste of time from the perspective of typical academic departments. And then also ew, why are you doing that? Real scientists don't go on TV. Real scientists don't host podcasts. They're busy writing papers and chasing grants. So most scientists do not engage with the public in any meaningful way. And this is a huge problem, because the science that does make it to the public can be easily distorted, easily twisted, and easily filtered. And so where the core values of science, where we prize things like healthy skepticism, reliance on the evidence, changing our beliefs as evidence changes, that gets lost in the translation, that gets lost in the shuffle. And then what comes out to the public is a series of authoritative statements where people use scientists, like politicians, major media figures. They use scientists as a source of authority, and strip away all the authenticity of science in terms of error bars and uncertainty and caveats and changing evidence and standards and limitations and all the stuff that makes science so robust. All that gets stripped away, and we end up making highly definitive statements. One example of how this played out during the pandemic was once it was becoming clear that the vaccines, the mRNA vaccines, were going to be successful. They were passing their trials. They were reducing, symptoms. They were saving lives in the trials, and the evidence was mounting for that. And that was a huge success story. That in less than a year we were able to develop a miracle cure.
The timing was pretty incredible.
It's insane. $1 billion investment helped. Also, decades of research that led up to the point. mRNA vaccines didn't just come out of nowhere in 2020. You can trace their origins back all the way to the early 1990s and the research paths that went to there. But what the message the public got from leading scientists, from public health officials, from even local health officials was stepping outside the bounds of the evidence. Because what the evidence said, what the trial said was, one, mRNA vaccines are not going to hurt you, at least not very much. And two, they're going to reduce your viral load. They're going to reduce your symptoms. They're going to improve your chances of living through you getting COVID. But the message, how that got turned in late 2020 was, everyone needs to get this vaccine and we can make COVID go away. That was the message. Mm-hmm. That was the communication. If you do this, COVID will go away. But that was beyond the evidence. We didn't know. We knew what the vaccine would do to an individual. We didn't know what it would do to a community. We didn't know if the virus would mutate and be more transmissible, but at a lower level. And so everyone got the vaccine, or lots of people got the vaccine, and then Omicron happened.
Yeah.
And we're still wearing masks, and we're still under quarantine, and there's still lockdowns, and we still have to report. And people are still dying, not nearly as much, but people are still dying. And people turned to the scientists and said, I thought you said this was going to make COVID go away. And that's because the message got distorted. We went beyond the bounds of the evidence. And that was because I believe the fundamental mistake here was that not enough scientists were communicating with the public, and not enough scientists were communicating what the science actually said.
I'm happy to say I'm starting to see, here in the museum, starting to see a shift in that. I'm starting to see more and more local researchers excited to work with the museum and to bring their message to the public. So maybe.
Absolutely. And the book isn't all like, doom and gloom and criticism. In the book, I use the book to showcase a lot of efforts, because there is a very slow, very generational sea change happening within the academic community, where many, especially young scientists, realize, our research is publicly funded. Maybe we should have the public on board with what we do, regardless of who's in the White House or in Congress. That's interesting. That's funny. And where a lot of senior academics just believe that they'll always be well-funded, we'll always have funding for science, we'll always have the support of the public, because for a long time, for decades, funding for fundamental research was bipartisan. Mm-hmm. It didn't matter who was in Congress, science was well-funded. But starting about 25, 30 years ago, that changed. And in fact, regardless of who's in the White House or who's in Congress, funding for science has been declining for 25 to 30 years.
I know NASA's budget has been taking some hits.
And then they'll get a short-term raise, but then it gets cut 4 years later. But if you look at long-term trends for NSF, National Science Foundation, National Institute of Health, the Department of Energy, the major funders of basic science, their budgets have been going down or flatlining consistently for 3 decades. So trust in science is down. Funding in science is down, and these are connected, I believe. And that's the argument I make in the book.
And you believe it can be reversed?
Absolutely. Absolutely. I have a lot of hope. I have a lot of trust in my fellow scientists that we need to engage in the public more. We need to teach them and show them what science actually looks like, which is wrong a lot, which is based on the evidence, which is always provisional, where we always change our minds. We update it based on things we learn, and that's what makes it beautiful. That's what makes it robust, is over the long arc, where people get an understanding that when they see a science headline, or they have someone in a position of authority saying what the science says, they understand where that statement comes from, and they understand the limitations of statements like that. And I believe that kind of honesty is the fundamental building block of trust, which hopefully leads to robust funding for science.
Well, I certainly hope you're right.
I hope I'm right. I think it's worth an experiment, because what we're doing now is certainly not working. We do need to engage with the public more. And it's through institutions like the Museum of Science here. We chatted a little bit before we started recording. I'm privileged and proud to call myself a friend of the museum.
Oh, we're very happy to have you.
And because what you're doing is connecting science and scientists to the public. You are that bridge. And it's not an accident that the museum sits on a bridge in
No,
Boston.
we actually do sit directly
literally
on
on a bridge. That's
literally on
how
top of a bridge.
synchronous is that. That's very powerful metaphor. And by being that bridge, by exposing the public to science, to scientists, to the scientific method, to the fundamental values of science, that it plays such an essential role.
And it's also just really fun to talk about.
It's also fun. Science is fun. Learning new things is fun. The universe is really fun. And bringing that joy is something that I deeply treasure personally.
Would you go into space if you had the chance?
Maybe.
Maybe?
Yeah, I actually feel no huge pull to go into space. In fact, I feel a pull in the opposite direction. It's gravity. That's just a gravity joke. I don't.
Oh my God. Wasn't that funny? Why am I losing it?
Yeah, because it was the funniest thing I've said. And so I set a really low bar and then like one mild funny thing.
Oh,
yeah.
Strategy.
I've been playing the long game this whole interview.
Oh, all right. Well, no, now I'm really gonna put you on the spot.
Yeah, I feel no great desire to go into space. I love thinking about space. I love taking my imagination and my mathematics and my simulations, my research, taking me to the edge of the observable universe, and I'm good. I'm good.
All right. Well, it's good to be happy with what you've got.
I like my feet on the ground, my head in the clouds.
All right. Now I'm really gonna put you on the spot.
Oh, wait. Okay.
That was a warm up.
That was a warm up on the spot. Okay, I need water for this.
Yep,
okay, hit me. I'm ready.
All right. Favorite sci-fi?
Babylon 5.
Oh, wow, that was easy.
That was easy. That was so easy. That was easy. There's no contest here. There's no contest.
I mean,
do I need to explain?
You do. You absolutely do not. Although maybe for people who don't know, because that is not, I love Babylon 5, but and in fact, there was a character named Talia on it for a little while.
Right. I remember. Yeah.
There wasn't a lot of Talias out in pop culture at that point.
No.
But for those who've never seen Babylon 5, you want to give a quick description?
Babylon 5, so 1990s show, contemporary with Deep Space Nine, who totally ripped off what Babylon 5 was doing. But that's a separate discussion.
Oh man, fighting words.
Yeah.
Words.
We're gonna get sharp here. Has not aged well in terms of watchability of like visual effects or staging or acting, all that kind of stuff, basic filmography. But what I found powerful, I watched it as a teenager.
Mm-hmm.
And so very transformative time in my life when I was like trying to figure out what I wanted to be when I grew up, trying to pick where I went to college. And just this was a show. The show centers on essentially a UN in space. There's a space station where in the aftermath of this horrific war, where many aliens and humans died, they try to set up a place where they can talk and where they can have dialogue and peaceful resolutions. And then, hijinks ensue for 5 seasons.
Hijinks ensue. It is a good show if you can track it down.
If you can track it down, it is so fantastic. If you can get past, it does look dated, but if you can get past that and sink into the story, it's such a beautiful story. And it was such a human story.
It was. I will say it picks up in season 2.
It does. It really does. And it was a human story, powerful human story, opened up some beautiful mysteries and questions, woven some things we wonder about the universe, but from a very approachable perspective. And I don't know, I cried at the finale. I was in tears. It was such a powerful show for me, and it stuck with me all these years.
All right. Well, on the note of having discussed that time that you cried.
Yeah.
I can think of no better note to end on than your tears, apparently.
That's awful. What an awful way to end the show. Okay, if you want to stick with that, it's your show.
All right.
Do you want me to cry right now?
Can you do that on demand?
I don't know if I have the acting abilities.
Although
I do have a little bit of allergies.
If you could just cry. I can't do that.
I'm trying. I'm choking myself up.
All right.
No, I'm okay. I'm okay. No, keep rolling. It's okay. I just need some water. But when they shut off the lights in the station and then it blew up.
Oh, man.
was so
Spoilers.
poignant. It was so poignant. They blow up the station at the end. It ended in like 1998. Okay, you don't need spoiler alerts for a 20-year-old show.
I suppose it's true.
Yeah.
All right, Dr. Paul Sutter.
I'm gonna go watch Babylon 5 now.
Yeah, thank you, Dr. Paul Sutter, astrophysicist, Babylon 5 fan.
Yeah.
Thank you very much for coming and chatting with us today.
I'm crying. I'm a little misty-eyed right now.
Oh.
Thank you for having me on, though.
Thank you again for coming.